Welcome to my Commodore 64 Games memories. This is where I look at old games and some of the technical details behind them. Let's get into it. Today we have Rampage, published in 1987 by Activision. Copyright by Midway. The developer was Catalyst Coders and Software Studios. Creators were David Jolliffe, David Wainwright, Mark Jones, and Michael Archer. I remember having this game on tape way back in the day, and as usual I'm going to be looking at this game in the C64 debug GUI and then using ICU64, which also uses Vice. This game was suggested by one of my YouTube subscribers, so let's dive into it. So yes, if you like these kind of technical deep dive videos, then please do consider liking or subscribing to this channel or sending me a super thanks. They are always very much appreciated. Here we are in C64 debug GUI and loading the disk version to start with. We get to this little screen here. It doesn't seem like much is happening, but there's actually quite a bit of drive code running in the background. And we can see that it's filling the memory. The memory view in the bottom left-hand corner, there is the C64 memory view, and the bottom right view there is the drive code view. Let's go to the full screen graphics view. So as the game is loading, we get this Activision Presents logo, and then we get quite a nice graphical bitmap loading screen. This, I think, includes a reproduction of some of the graphics from the original arcade version. So the surprising thing about this game, as we'll see, is that it actually allows up to 3 players. And the 3 players are actually quite large sprites. This game does take a while to load, even on disk. We can see from this debug view here that it's definitely a bitmap. We can see that there's just a ton of code running. To be honest, the drive spends most of its time up in its own version of the ROM code. We can see that from the memory addresses on the right-hand side there, which are the drive code memory addresses. Eventually we get to this other screen where we see our 3 main characters that are player controllable, George, Lizzie and Ralph, which I think is yet another bitmap screen. Then we get to this screen telling us to collect various items. So this is just a normal text screen. Nothing really special in here. Pressing fire brings you to this screen and you can choose to start 1, 2 or 3 players. It waits for a little while for the corresponding players. Now here we go. We can see these red borders around the sprites and indicating that we've got at least 2 by 4, so 2 sprites horizontally and 4 sprites vertically for each player character. This means that when 3 player characters are next to each other on the same horizontal position on the screen, then we have up to 6 horizontal sprites being used on the same scan line for all 3 players. Now the Commodore 64 has a limit of 8 hardware sprites in a horizontal band. So this means that the remaining 2 sprites that we can see there, the helicopters, the buses or the trains or the tanks, as we can see zooming around at the bottom, and the police car, the emergency services vehicle, those extra objects are basically using up to 2 sprites. However, those 2 sprites are multiplexed, so we can have 2 sprites used up at the top of the screen for the helicopters in silhouette, and then further down the screen we can have the helicopters whizzing around in the middle, and then we can have the tank or the police car or whatever it is moving around at the bottom of the screen, as long as they don't all try and appear in the same horizontal band. So using the sprite multiplexing for the remaining two sprites, we can actually have freely moving and independent objects in addition to the three player objects. Using the debug view here, which shows us what sprites are active at what scanline positions, as I move the targeting cursor up and down, we can see that the sprites are updated at different times on the raster position, and there's quite a lot of code running there which updates those sprite sheets. Now, the game is actually flickering quite badly. I think when it's running in C64 Debug GUI, it's actually struggling for some reason. Maybe I've updated some part of the memory or something like that, or maybe it's just not cooperating that well in C64 Debug GUI with that flickering screen. I don't remember the flickering screen in the real game version there, so I think that's probably an artifact of running in this particular emulator. So the impressive thing here is that we have these 2x4 sprite grids for each of the three players. So that's quite a lot of sprites, right? Let's concentrate on one of the player characters. Now, if I move this targeting cursor up and down, we can see how the code on the left-hand side there is starting, well, it's certainly doing quite a lot of memory copies at the moment with those load and stores indirected. But as I move the targeting cursor up and down, we can see as this raster position moves down the screen, then the sprite grid is updated for the player character. And also the multiplex sprites, those two extra sprites that we have, are being multiplexed for the helicopter and then the police car. The last part of the sprites, the player character there at the bottom of the screen, was actually showing that it switches to some empty sprite definitions right down here. We have quite a lot of code running which updates these sprite grids, but also updates the multiplexed sprites. Those sprites that are highlighted in light blue there, cyan, I think, those are appearing in the border. So as I force the sprite colors there, we can see that the silhouette helicopters are appearing there against the black background, but the helicopters, when they're in silhouette, of course, are black helicopters, so we need to see those. So these helicopters and the police car are definitely using some extra sprite multiplexing. We can see that the first two sprites, sprite 0 and sprite 1, in the debugger here, are being shared for the helicopters, the police car. As I move the targeting cursor up and down, the targeting cursor basically represents what's going on the screen at this particular point in the raster position. As I move the raster position left and right across the characters, we can see the instructions on the left-hand side that are executing at that particular point on the screen. So we're getting a load of load and stores indirected with 8b and 8.9, and 8.9 is storing into the low and high bytes there are 10 and CF, so swap them around, we get CF10, and we're storing into CF10 with whatever's in the Y register added on, so that's 2A. So it's updating quite a lot of data. We can see here that the sprite registers now are updating the sprites for sprite index 0 and 1. These corresponding registers here, D000 and D002, are the sprite X positions for sprite 0 and 1. Let me just bring that up in the include file that I have here for my development, and yes, that's the first two sprites. And then here we've got D001 and D003 there, which updates the Y position. And we can see this, we can see the sprite positions being reflected in the visible debug screen there as we move left and right, up and down. For the raster position, it changes the position in which where the code is executing, of course, in terms of time. Don't forget that the raster beam, which is synchronized to the VIC chip output, the video chip output, is left to right, top to bottom, 50 times a second in PAL, in the PAL display for this PAL C64 version of the game anyway. In NTSC, of course, it is 60 frames a second approximately, but I tend to use PAL versions of games because I grew up with the PAL C64. As I move the targeting cursor up and down here for the raster beam, you could see that the character sets were changing here. So we have two character sets. The character set used for the top of the screen, which is used for the score and damage indicators. And then the character set changes to be the character set used for the background. The thing that young me really liked about this game was that when you destroy the large proportion of the building actually crumbles, and you can see that it reveals the background behind it. So you could see that it was revealing the tree, for example, or the lamppost when the building in the foreground crumbles away. I thought that was a really neat effect in this game. Very well coded, actually. So let's hop now into ICU C64 or ICU 64, which of course uses a different version of the Vice emulator, but it allows debug views of the memory view, the graphics map, the text screens, bitmaps, sprite views, for example. It also has a much easier to use machine code monitor as well, which will help us out. In this version, I'm looking at the tape version now rather than the disk version. The tape version certainly has some loading screens as it is loading the game, but of course we've got the usual kind of flashy border effect where it just shows that the tape is actually loading information from the screen. We get to the same kind of screen there where we can choose how many players we have. But let's start using the graphics debug view windows here to actually see what we get. Now, straight away, I can see that we have some dynamic sprites up in the last VIC bank there, the VIC bank which starts at C000. I can see what looks like some temporary working area for dynamic sprites, and then those sprite areas are then being copied to the real sprites, which are then visible with the VIC chip. So that first bank of data there looks like it's structured data, but it's not quite sprite structured data, and I don't think it's quite character set structured data. It looks like it's something in between, and I think it's quite unusual that it would be using that area of memory as temporary working space area for what looks like the target dynamic sprite frames. But definitely this game is using dynamic sprites. Basically, when I say dynamic sprites, I mean that the sprite graphical data in the VIC bank is being updated, either decompressed or updated by code, instead of having all of the frames there in memory in the same VIC bank and just changing the sprite pointer. The actual graphic data for the sprites are changed, and the underlying sprite pointers are probably not changed. I mean, it's still updating the sprite pointers when it updates the sprites for the sprite sheets, but it is not just having all of the graphics data all in one go. And that's because we can see that we've got graphics data for the individual graphics frames for the helicopters and the airship and the police car and the train, etc., and the tanks, of course. Let's get that building in the foreground destroyed and see if we can reveal the building behind This is a really great effect, isn't it? It's really surprising that with such large player character sprites, we're still getting quite a lot of background text screen updates for the buildings collapsing. There we go. And then the trees behind get revealed. And then that's the end of the level. And now we get to the next level for the game. So the next level for the game is pretty much the same kind of thing, but we have a different layout of buildings. And I think for this game, the layout of buildings, that's the challenge, right? Because you need to know how to destroy enough of the buildings to get them to collapse and then reveal the buildings behind, so then you can work on those buildings and getting them damaged enough for those buildings to collapse, while, of course, picking up the objects. Now we can see here from the machine code monitor that definitely the video memory is where we expect. So let's put the graphics debug map. Let's find that text screen information and also the characters in the debug graphics map view there. So that's surprising, isn't it? Although it looks like a static game screen, it's actually not. It's actually using two double buffered screens, and we can see that actually there's quite a lot of overdraw happening, and the overdraw is evident because we're getting quite a lot of flickering between these two double buffered screens. And one screen is at E400 by the looks of it, and the other one is at E800. So it's drawing the score, it's drawing the buildings from back to front, it's redrawing everything, actually. Wow, that's actually quite a lot of redrawing going on. Let's look at the debug view now for the character sets, because I can see that there's actually a little bit of updating going on there as well. So let's have a closer look at that. So if I switch it to multicolor view and unpause the game, it's actually a lot easier to see. There we go. So here we have updated characters in one of the character sets used for the background for the bullets. It seems to be doing a masked bullet draw, so we have a maximum number of bullets by the looks of it, and the bullets that are coming from the helicopters or the tanks seem to be taking a copy of the previous the underlying background characters and then overlaying the bullet graphics on top of that and then updating that into there. We also seem to have a whole bunch of character set data for the intermission screen for the player characters. Those are the player character little mini pictures, if you like, for each of the 3 player characters. So that's interesting. So there's actually quite a lot of graphical data being updated by this game for every single frame. There we go. I'll zoom in and then we can see the dynamic bullet characters. Yes, it's definitely the bullets, and it's definitely, look, it's masking with the background data as well, so it's pulling the desired background character set definition and then plopping the bullets on top of that. Those are definitely the intermission player character graphics there as well. So this area of memory here doesn't quite look like sprite data, but it's definitely well structured. In the debug memory view there, I can see quite a lot of repeated green reads from what looks like 4000 in hex. I'm pretty sure that that's where the source data for the player character sprites are being copied from, and I'm pretty sure that that's where the yellow bar there is where it's compositing that data into its destination sprite Vic bank data. This data looks like it's structured, but it's not structured in terms of sprite data. I'm just using the graphics sprite debug map view there. Let's look at it in terms of bitmaps. So the 4000 in hex, aha, well, there we go. Immediately there, we can see that this data, let's zoom in a bit here. We almost have a full Vic bank of what looks like character formatted data or bitmap formatted data, which is basically the same character set data. which those individual character set definitions, if you like, character definitions get copied and composited together by the player sprite animation routine to form the large 2x4 sprite grid arrays. It goes into this memory address here. Look, it's updating that one constantly. It's updating. I'm trying to draw over the top of it, you see, with the debug view in the graphics sprite map there, and it's rewriting the pixels. The sprites which don't get dynamically updated obviously retain the pixels that I'm drawing over the top of them, but yes, that composition, that temporary composition data memory there. So it's probably, from an optimization point of view, it was quicker for the code to temporarily composite the player sprites together into this area of memory and then copy them into visible sprites. Rather than trying to do everything in one go, it's probably easier to put them into temporary space. There even might be some caching information or previously cached sprite frames in there or something like that as well. But it's probably just a data geometry optimization step there. Because copying from character-based graphics, like we have there in the bitmap graphics map debug view there, into sprite data requires a different memory structure of the data, because character definitions and sprite graphics definitions are not stored in the same way. The bytes are stored in different ways. There may also be some hardware flipping. There may also be some software flipping of the dynamic sprite data as well in this composited temporary working space. So I'm really intrigued at how much this game is actually drawing for what looks like a static background screen. It's actually doing continuous redrawing of the entire game screen from back to front. So it's rendering the buildings in the background, the silhouettes. It's then rendering the individual buildings with their individual damage from back to front. It's calculating up to 3 sprite player frames and then updating those dynamic sprites into their final position in the dynamic sprite Vic bank before then displaying the entire game frame. So it's doing quite a lot of work. It's doing an awful lot of work, actually. So I think we'll leave this video there. I think I covered everything that I wanted to cover for this game. The surprising amount of work that it does on the game frame is quite unusual for a game from this time period. If you like these kind of videos, then please do consider liking or subscribing to this channel, and a super thanks is always very much appreciated. Thank you very much for watching. Take care. Have a great day or evening or night, wherever you are.